what I want to tell you about today is how surfaces that shed water could have a significant impact on global energy in the future, particularly their efficiency. The condensation of water on surfaces is responsible for air conditioning in large modern buildings. It's also used to make 50% of the world's desalinated water, and most importantly, it's responsible for 85% of the global production of electricity. In the year 2011, an astonishing 22,000 terawatt hours of electricity was produced, and the aggregate efficiency was only 32%. This is nowhere near the thermodynamic limit. If we could improve that efficiency just 1%, we could make more electricity than all the installed solar to date, and that includes both photovoltaics and concentrated solar power. Inside a power plant, water is continuously cycled, and it transforms in phase from liquid to vapor and back again. To boil the water, you can use a variety of sources. Old-style plants use coal or perhaps natural gas. Newer technologies, nuclear, including the cycle that Leslie showed us yesterday, as well as concentrated solar power, all provide the heat that boils the water. You've created now high-pressure steam, which expands through a turbine that rotates a generator producing electricity. And what we're concerned about is the steam that exits the turbine. That needs to be condensed back to liquid water. And that really happens on a massive scale. Every year inside these cycles, the equivalent of 10 trillion gallons of water is condensed. That's the equivalent of the amount of water that's in Lake Mead. So it's really important to get the details of this activity in the condenser correct. And in particular, we'd like to have the best possible heat transfer in the condenser. We'd like the temperature in the condenser to be as close as possible to the temperature of the cooling water, which may be a river or an ocean. The closer that temperature differential is to zero, the closer we'll be to thermodynamic efficiency. In current condensers, the insides are metal, and water wets metal, so it forms a liquid film on the surface of these of this metal. And that actually is an insulating layer. Water is a good insulating layer, and that reduces the heat transfer, giving us a relatively high delta T across the condenser. If we modify that metal with a very thin coating, we can create hydrophobic behavior. The water beads up, and in the open area between the droplets, you now have excellent heat transfer directly between the steam and the solid surface. And in fact, you get an enhancement of over a factor of 7 by this method. It's essential, besides being hydrophobic, that the coating is also ultra thin, or otherwise the coating itself acts as a thermally insulating layer. The third requirement for implementation is that it's durable. If the coating only lasts a short time, it's not really practical. So what you're seeing here is a side-by-side comparison of a conventional coating using a fluorosilane and the coating developed in my lab using ICVD. At the beginning, both exhibit this desirable dropwise condensation, but what you can see for the fluorosilane is that it quickly degrades. In fact, it delaminates and exposes bare metal, and you're back to this film-wise condensation. Where the ICVD film, there was a break in the action, and you're now at 48 hours, 2 days later, and you're still in this efficient dropwise condensation mode. And this can be quantified, and this data was taken in the lab of my colleague, Professor Kripa Varanasi, and you're looking at heat transfer coefficient as a function of time, where there's a discontinuity on the time axis so that we can get out to 48 hours. And what you can see is that our ICVD coating displays the same heat transfer rate independent of time, where the traditional coating only lasts for 2 minutes. There's a tremendous drop, and it decays down to bare metal. The 7x increase in efficiency that we achieve for the heat transfer coefficient correlates to a 3 to 4% increase in the efficiency of the steam power cycle overall. And that amount of energy mid-range, 750 terawatt hours, besides being a massive amount of energy, also saves a tremendous amount of carbon. It's the equivalent, if this was done globally on every power plant, of not having to build 150 coal-fired power plants. It's also the equivalent of not having to plant the area of 4 times the state of California with forests. The technology in my lab is derived from chemical vapor deposition processes which run at higher temperature in the semiconductor industry. And we know that that's always scaling to larger wafer sizes. We've developed a low temperature process which allows us to make the hydrophobic materials. They're ultra thin, only 30 nanometers thick. They're currently been commercialized in the manufacture of tires. The coating is used on the molds that are used in the manufacture of tires and allow for the easy release of the rubber from the molds. This is a picture of a reactor which is already greater than a meter across. So you're ultra thin, but over quite large areas. And one of the key features that makes this coating durable is that we actually create covalent chemical bonds between the solid surface that we're modifying and the coating itself. And that chemical bond is what leads to the durability. In this picture, we see a prototype in our lab. It's not only important that we get to a large area, but it's also important that we coat the shapes that are important commercially. And this is actually a copper tube, which would be a heat transfer surface. You see the dropwise condensation is maintained even over 4 hours of operation, which is the patience of the graduate students that are currently running this. Here's a picture of the realistic condenser geometries. These are banks of tubes, and they're several meters across. You can see people standing there. We need to be able to coat this geometry, either individual tubes or banks of tubes. We need to do this over several meters, so we still have a challenge of scaling this technology further, but I think it's not such a stretch to go from 1 meter to 10 meters. So what is the pathway forward? I think there's 3 essential steps in order to get to deployment. The first is that we need to do more extensive lab-scale evaluation of realistic conditions. Everyone wants to torture our coatings in slightly different ways, and there are additives in the steam cycles. Additionally, we need to build that bigger machine, the bigger CVD reactor that will enable us to do the coatings. And we need to understand the maintenance cycles for the power plants. And we need to partner with a power plant in order to evaluate this in a realistic condition and have the data that convinces people that this should be deployed globally to save this tremendous amount of energy, 750 terawatt hours, and over 500 million metric tons of carbon dioxide. And not to mention the thermal pollution that's saved because you have less waste heat. And I believe that this is really a tremendous piece of the portfolio that could move us towards a sustainable energy future for planet Earth. Thank you very much.